Okay, this is a tutorial on metallic bonding, and we're going to be looking at the electron C model of metallic bonding and how that can explain such properties as malleability, conductivity, and luster. So the properties of metals can be understood by looking at the atomic structure of metallic bonding. But first let's get reacquainted with the ionic bond, because if you understand the ionic bond, that's going to make it a lot easier to understand what the electron C model is telling us. So here we have a metal reacting with a nonmetal. The transfer of the electron, the reaction, results in a positive ion and a negative ion. So the ionic bond is simply the electrostatic attraction between the positive and negative charge that the ions have. So you could call this a sodium atom and this a chlorine atom, and once the sodium loses an electron it becomes Na+, and the chlorine gains that electron and becomes Cl-. So the sodium ion and the chloride ion, being oppositely charged, are electrostatically attracted. And so that opposite charge results in a crystalline structure where we have an ongoing array of alternating positive and negative that are all attracted to each other, and that keeps the crystal together. Let's look at the arrangement of atoms in a metallic crystal. Very similar to the organization of an ionic crystal, however, they're all positively charged. And just looking at this illustration, you would think that the atoms would completely fly apart by repelling each other due to the positive charge. But if we take a closer look, the electron C model tells us how the positively charged cations in the metallic crystal can stay together. So as an example, we'll take a look at aluminum. Looking at the subatomic structure, we can see each aluminum atom has 13 protons but only 10 electrons. It has given up the 3 valence electrons to what is called the electron C. This is why it's called the electron C model. The space in between each atom is filled by the valence electrons that have been given up by each metal atom. So the metal atoms become cations, positively charged ions, and the valence electrons are loose in the spaces between the cations. So what's holding the crystal together is the electrostatic attraction between the positively charged cations and these free-floating negatively charged electrons. And so the valence electrons are not localized to any one particle. They are free to move and occupy the space between the positive ions. And so similar to the electrostatic attraction that holds the ionic crystal together, we have this attraction of opposite charges that are holding the metallic crystal together. So aluminum giving up 3 electrons means that all the cations have a 3+ charge, and each aluminum atom has contributed 3 electrons to the sea of electrons. This creates quite a strong attraction, and we can use this model as a way to explain various properties. For example, there is malleability, the ability to put pressure on a piece of metal and not have it break. So we can pound metal with a hammer, we can pound it into a shape and not have it break. How can this model explain that phenomenon? Well, let's hit it with a hammer and see what happens. Ooh. One last blow. Okay. So as you can see, the atoms were shifting. They didn't break apart. Hitting the metal with a hammer does not break it. Why would that be the case? Well, the delocalized electrons are always there. So any shifting positive ions are going to be able to be held together by their attraction to the constant presence of those valence electrons, that sea of electrons that the atoms are attracted to. And malleability, of course, is also intimately related to ductility. You can force the metal into the shape of wires. So this is malleability. And a nice contrast would be to look and see, why does hitting an ionic crystal not result in this sort of malleability? When we hit an ionic crystal, it shatters. Let's hit this ionic crystal with a hammer and see what happens. So no matter how you hit it, you're always going to come to some point where like charges are lined up. And so if like charges are lined up, the result is going to be a great deal of repulsion, and that's going to split the crystal. And when ionic crystals cleave, they often leave a very sheer, smooth face if you do it carefully because of the way the opposite charges line up. All right, back to metallic crystals. So why would this very strong attraction result in other properties? How about their strength and high melting point? Well, the atoms want to stay together. They're very attracted to the sea of electrons. And so therefore, the higher the amount of valence electrons given to the sea of electrons, the tougher the metal, the harder it is, and the higher the melting point. Transition metals in particular, like titanium and molybdenum, each of which contribute a large amount of valence electrons to the sea, they are very tough metals, very strong, very high melting points. How about electric current? Can this model explain that? Well, electric current is simply the movement of charge, and electrons are constantly moving through these spaces between the cations. They therefore are very able to carry an electric current, and that also explains their heat conductivity, the fact that they can move through the crystal. And what about the shininess, the luster of metals? If you think about where light comes from, the emission of visible light from electrons, well, the sea of electrons, these valence electrons, can very readily absorb and re-emit visible frequency photons, and that makes metals very shiny, very lustrous. And so here's an example of a giant structure, a sculpture in Chicago called the Bean. It's extremely shiny. It's made out of stainless steel. Is primarily iron, chromium, usually a little bit of nickel, definitely some carbon, and depending on the stainless steel, a few other metals thrown in, all engaging in metallic bonding. So the shininess comes from the ability of the stainless steel to easily absorb and re-emit visible spectra of light. But what's interesting about that is if you think about what would happen if you put a scratch in the bean. Well, you would see that scratch because it would scatter light. So it would no longer be shiny right where the scratch is, right where there's an irregular surface. And an irregular surface will scatter light in different directions. So the shininess of any metal does depend on how smooth the surface is. If it's a scratchy, non-smooth surface, then you don't get that shininess.